8.2.1 Rankine Cycle. The Rankine cycle is the model for vapor power plants. It is the basic foundation for actual vapor power plants. The Rankine cycle consists of 4 steady flow devices, including a turbine, a condenser, a pump, and a boiler. Water is the most commonly used working fluid for the Rankine cycle. The main objective in analyzing the Rankine cycle is to determine the thermal efficiency. To do that, we first need to understand the Rankine cycle components and the corresponding thermodynamic states. Then we will determine the amount of work and heat interaction in each component. We are going to assume all 4 components are steady flow devices. The turbine and the pump operate adiabatically and reversibly. We neglect the kinetic and potential energy changes in each component. We are going to apply the energy balance on each component. For a turbine, no heat transfer, no kinetic energy change, no potential energy change. Energy balance is reduced. Work output by the turbine is H1 minus H2. 1 is at the inlet of the turbine, 2 is at the exit of the turbine. For a condenser, there is no work associated with the condenser. No kinetic energy change, no potential energy change. Heat output from the condenser is H2 minus H3. 2 is at the inlet of the condenser. 3 is at the exit of the condenser. For a pump, no heat transfer, no kinetic energy change, no potential energy change. Work input required by the pump is H4 minus H3. So 3 is at the inlet of the pump. 4 is at the exit of the pump. For a boiler, no work is associated, no kinetic energy change, no potential energy change. So heat input to the boiler is H4 minus H1. 4 is at the inlet of the boiler. 1 is at the exit of the boiler. The ideal Rankine cycle consists of 4 processes. Process 1-2 is an isentropic expansion in a turbine. So the saturated vapor enters the turbine, it expands isentropically and produces work. Process 2-3, heat rejection from the condenser at constant pressure. The saturated mixture enters the condenser and rejects heat to the surroundings. Process 3-4, isentropic compression in the pump. The state 3 is the saturated liquid. The liquid is compressed from state 3 to state 4 isentropically. Process 4-1, heat addition through the boiler at constant pressure. The compressed liquid enters the boiler and is heated at constant pressure. The saturated vapor enters the turbine. This completes the cycle. The area under the process curve on a TS diagram represents the heat transfer. The enclosed area 1, 2, 3, 4, 8, 1 is the net heat input or net work output per unit of mass flowing. The phase of the working fluid in the process 3-4 is liquid. There is negligibly small change in the specific volume during the process. So we can assume the specific volume at state 3 equals the specific volume at state 4. So the pump work is expressed as this. Pump work is approximated as the specific volume at state 3 times pressure change between the state 4 and state 3. There are some commonly used performance parameters in the cycle analysis. The thermal efficiency of the Rankine cycle is defined as the net work output divided by the heat input. The net work output is the work output by the turbine minus the work input to the pump. That is also equal to heat input minus heat output. It can be also expressed in terms of enthalpy. So basically, we need to know the enthalpy of the working fluid at all states to determine the thermal efficiency of the Rankine cycle. Back work ratio is defined as the pump work input divided by work developed by turbine. Small back work ratio indicates small pump work is required compared to the work produced by the turbine. Example 8.1. Steam is the working fluid in an ideal Rankine cycle. Saturated vapor enters the turbine at 8 MPa and saturated liquid exits the condenser at a pressure of 0.008 MPa. The net power output of the cycle is 100 MW. Determine for the cycle the thermal efficiency, back work ratio, mass flow rate of the steam, the rate of heat transfer into the working fluid as it passes through the boiler, rate of heat transfer from the condensing steam as it passes through the condenser, the mass flow rate of the condenser cooling water, if cooling water enters the condenser at 15 degrees Celsius and exits at 35 degrees Celsius. We should be able to sketch the processes on a TS diagram for better understanding of the problem. Note that the processes in the pump and the turbines are isentropic, and the condenser and the boiler go through constant pressure processes. We'll need to know the enthalpy at each stage for calculating various quantity in this problem. So I'm going to make a table to organize the data. So we have 4 different states. Second column is pressure in megapascal. Third column will be temperature, quality X, entropy, and enthalpy. At state 1, the pressure is 8 megapascal, and saturated vapor enters the turbine. So quality is 1 at state 1. We also know that saturated liquid exits the condenser at 0.008 megapascal. That is state 3, 0.008 megapascal. And the saturated liquid quality is 0. We know that in the boiler, pressure is constant. So state 1 and state 4 are at the same pressure. Also in the condenser, the pressure remains constant. So state 2 and state 3 have the same pressure. So this is all we know from the problem statements. Now let's complete the tables. At state 1, we know the pressure and the quality, so we can fix the state. So see table A3. At state 1, 8 megapascal or 80 bar, and saturated vapor. We have enthalpy H1, entropy S1. At state 2, the turbine operates isentropically. So S1 equals S2. S2 is also same as S1. So at state 2, now we know pressure and entropy. So we can also determine the enthalpy at state 2. So at state 2, pressure is 0.008 megapascal or 0.08 bar. So entropy 5.7432 is between these two numbers. So we can determine the quality at state 2. So quality 0.6745. So now we can calculate the enthalpy at state 2. H2 So enthalpy 2 is calculated. At state 3, we know pressure and quality, so we can fix the state. At 0.08 bar, enthalpy for the saturated liquid. This is H3. And entropy at state 3. At state 4, we know the pressure, 8 megapascal. And the pump operates isentropically. So S3 equals S4. So S3 is here, S4, the same as S3. We know that state 4 is compressed liquid. The property at state 4 is approximated by saturated liquid. But the temperature at state 4 is unknown. And we know that the pump work is approximated by the specific volume at state 3 times the pressure difference P4 minus P3. So we can solve it for H4. So pump work is approximated by the specific volume at state 3 times pressure change between the state 3 and state 4. This is the work input required by the pump. And this is same as H4 minus H3. So we solve it for H4. So enthalpy at state 4 is calculated. 181.94. So now we determine the enthalpy at each state. Now we are ready to solve the question. First, determine the thermal efficiency. Thermal efficiency of the Rankine cycle. H1 minus H2 minus H4 minus H3 Now we know the enthalpies at each state, so plug in the values. So the thermal efficiency of this cycle is 0.371 or 37.1%. The Rankine cycle is able to convert 37.1% of the heat input to net work. So you may think it is quite low efficiency. In this problem, the Rankine cycle operates without irreversibilities. So the actual vapor power cycle would have even lower thermal efficiency. So the second question, determine the back work ratio. So back work ratio is also expressed in terms of enthalpy. So the back work ratio is 0.00837 or approximately 0.84%. So it is typical that the vapor power cycles have such a low back work ratio. This means only the small percentage of the turbine work is used to operate the pump. Determine the mass flow rate of the steam. In the problem statement, the net power output of the cycle is given, which is 100 megawatt. Net power output per unit mass flowing can be also expressed in terms of enthalpy. So this is the work produced by the turbine. This is the work consumed by the pump. And we solve it for mass flow rates of the steam. So let's put values in. So this is the mass flow rate of the steam. Determine the rate of heat transfer into the working fluid as it passes through the boiler. So basically it asks to determine Q dot in. So we just calculated mass flow rate of the steam, and H1 and H4 are known. This is the heat transfer rate in the boiler. Determine the rate of heat transfer Q dot out from the condensing steam as it passes through the condenser. So basically, we need to determine the heat transfer rate in the condenser. We know all the quantities. So this is the heat transfer rate in the condenser. Lastly, determine the mass flow rate of the condenser cooling water. If cooling water enters the condensers at 15 degrees Celsius and exits at 35 degrees Celsius. Condenser is a type of heat exchanger. So there exists heat exchange between the cooling water and the working fluid water. So let's say this is a condenser, location 2, location 3. So the working fluid water enter and leave the condenser. There is also cooling water flowing across the condenser. It enters the condenser at 15 degrees Celsius and leave the condenser at 35 degrees Celsius. So we can apply the energy balance equations on the condenser and determine the mass flow rate of the condenser cooling water. So condenser is our system. Energy balance equations, mass flow rate of the cooling water. Assuming the condenser is an adiabatic device, there is no work associated with the device. And we just calculated the heat transfer rate in the condenser. So we can solve it for the mass flow rate of the condensing water. So enthalpies of the condenser cooling water entering and leaving the condenser are approximated by the saturated liquid at 15 degrees Celsius and 35 degrees Celsius. So see table A2. At 15 degrees Celsius, the condenser cooling water enter the condenser and leave the condenser at 35 degrees Celsius. So this is H, cooling water in, H, cooling water out. So we solve it for the mass flow rate of the condenser cooling water. So this is the mass flow rate of the condenser cooling water. So in these questions, we use the tables and write out all the known informations and determined the enthalpy at each state. It is very helpful to create the table, something like this, to determine the unknown quantities.